every single byte has a different address, and every single byte is also made up of 8 bits. You already know, I won't be going into that much depth. But and the address typically here in a like in this memory, heap memory has is a hexadecimal number. You know, like hexadecimal number, you already have read about that. So let's say, and like typically for this kind of data types, the memory is contagious, like it's continuous, it's not here there. Okay, so suppose here, I'm like, let's consider here the it's one, it's two, like typically like this, like this, like you'll be knowing that it's 3 and 4. So typically for every contiguous memory location in CPP and like similar languages, the first address is considered, because after looking at the data type, it automatically gets that the next 4 for like double, it will be next 8, for long it will be next like 8 and stuff. So this is how it gets to know that the next 4 locations will belong to this int only, the number 5. So what it does is that here it makes a mapping like this, that num, and it's mapped to what, suppose this address, it's actually not one, I'm just writing here for reference and stuff. But yeah, like it's one here, it's like it maps it that it's one. It's a bit up and down, but yeah, you're understanding what I'm telling. Now you understand that this is how this is stored, and here it's like the 5 is written here, like all these memories store the 5. Now there's a operator in CPP known as the ampersand, like which looks like and operator. It's the ampersand operator, and what it does is that it helps you to get the location of the, like the address where the data is stored. So let's try this out. It's int num equals 5. So if I write cout um, ampersand num endl, it's okay, typo. And if I run this, run code, you will see a hexadecimal number is given. So what it basically means, if I copy this one, here the this one is this address, the first one is the address, and the other one are the other contiguous ones. Okay, now this is how addressing works in the CPP. Now why is it typically like needed for linked list, you will get to know after a while. So, and to store the address and stuff, and like there's a different kind of notation, or what to say, a kind of data type which are known as pointers. Now you have seen that I have written ampersand num, and that gives the address of the like the data stored. But what if I want to store it? So there's a typical notation here which known as, if I say like int star, I will explain the whole thing, equals to ampersand num. So here ampersand refers to the, like the address of the thing, and typically the star given here is known as the dereferencing operator. Basically what this means is that you can read it as value of. So I will explain it here that what happened. So let's move this thing downwards. So if I write here int star ptr equals ampersand num, so here in the memory a similar kind of ptr variable is created. Okay, and I'll be talking about the like the space needed and stuffs after a while. So here the address, this address is stored here. Okay, now you're wondering why is this useful. Now this dereferencing operator, the star present before it, makes the variable of a type that the variable doesn't directly return the value present in it. The variable returns, like it considers the value present in it as an address, and makes this thing, like supposed to say, it makes this thing points towards the actual address, which is this one. So it's actually like address of this one, and when you attach a star here, like I'm just for visualization I'm writing doing it here. It points to this one. So what it does is that ptr stores the ptr in like in itself stores the address of num, and as it is a dereferencing of operator, it points towards the address of num, thus making the like. And typically if you now write star ptr, now ptr stores this value, but if you write star ptr, it will print the actual value of num, that's 5. Now let's print both the things, ptr and also star ptr. You'll get to know about the difference. So and if I run this code, run code, you will see this prints the same address. So basically ptr and ampersand num prints the same address, but star ptr, as I told, it dereferences, it points to the value and goes to that value and finds out that value. So it goes and finds out that okay, in the like c24 whatever, the value present is 5, and then it prints it. Now let's talk about how the naming of int star ptr ampersand num comes. So basically the first data type present here is basically the type of data we will be pointing at. Okay, now here we are pointing at a num, which is the int type of data, so that's why it's int star ptr. If it would have been a double, it would have been like worked similarly, only the difference would have been that the type would have been like, it would have been double star ptr. If you want then I can do it, but it's like it's just the similar thing. Now let's see what this. Now you typically know that a int type of variable takes 4 space, but for pointers every pointer takes 8 space. For proof I'll be console logging it here. It's size of ptr, size of ptr, it's basically the address. So the address takes 8 space, and it does like it doesn't matter which data type it is, it will take 8 space irrespective of the data type. And if I write in the same way, if I write here star ptr, okay, okay, size of, sorry, size of, you will see it's 8. The this one I'll be commenting out the previous ones. No, it's okay. So it's typically 8, and it's typically always 8 because it stores the address, and the address is like 8. So yeah, let's mm, dive deeper into some more concepts of pointers. So other than that, let's see some typical stuff. If I just write here, you guys are familiar with this thing, int num equals 5, and say int a, I declare another variable and keep it the same name like num like the same value 5. Now if somehow I like increase the value of a plus plus, you guys have seen that the value of num remains unaltered, just the value of a is changed. And why this happens? This happens because both of these have like occupy a different memory and they are independent. It's just a shallow copy, just the value is copied. But whereas if I just do here, I have redeclared num twice, it will give an error. So yeah, let's still print it here, cout a, and if like if the pace is a bit high for someone, you can just write in the chats, I will check it out. And if you have any doubt, you can also reach out here. So if I print out these two things, it's like very basic. And so you can see that here the value has changed for a, whereas for here it hasn't changed, it's the same. So it was a shallow copy. Now if at the same time what I do is that if I write here int star a equals to ampersand num, okay, and I do a star plus plus plus, let's see what happens. Wait, okay, sorry. It started. Wait for a bit. Star plus plus. Okay, wait. Okay, wait for a bit. Let's understand the difference here. So you will see that here I have increased the value of a, which is not actually num, but the value of num has also increased, which wasn't happening previously. So let's understand what happened. So let's make another heap. It's getting so let's say here was a variable, as here said num, and it had an address, suppose 5. Now we created another variable here which was named a, which had the value 5 here, and which was directly referencing to this variable. It was directly pointing to it. So when we increase the value by saying here uh, when we increase the value of star a, which directly pointed and was holding the power to change it, then what happened is that the value at 5, which was previously appointed 5, like it's, let's say the value here that was present was 10. Okay, was 10. So here what happened was that the first, when we said let's write a bit more. This is a, this is num. Okay, now when we did a, if we have done a plus plus, what would have happened is that the 5 is just a variable, right? It's it's a address. Now what happens on increasing is a different topic I will discuss after a while. But what happens, we use star a. So star a directly points here, as you have seen. So and star a means this value, that's 10. So when we went there and increased that value, that increased the value at that respective location it was supposed to be, which was the value of num. So after what was happened was there, the actual value of num was increased. Now let's understand what happened when it did the shallow copy previously. In shallow copy previously, two totally different entities were created. So either and the value was just given to that, so it doesn't matter whatever value I change and stuff, like it remained the same, the value of num. Now I think it's clear for you. um, Now I'll be showing how to copy a pointer. So it's pretty easy. Like, you have seen that I have to declare another pointer q, and here you know that the value, what I was doing previously was I was assigning an address of a different variable here. And if I want to copy a pointer, like have a similar kind of pointer, you know that ptr holds the value of ampersand num. So it's but star ptr holds the value of num. So what I have to do is that it will just be ptr, because ptr is similar to ampersand num. For proof I'll be printing it here. P, let's have something here. Q, star p, star. Okay, it's not p, it's ptr. Wait a bit. ptr, ptr, yeah, now it should work. Yeah, here, yes. Let's run this code. See, f4, like check the last three values. These all are the same. Okay. So now we have also learned how to copy a pointer. Now, now let's understand. Now, as you have seen, like similarly as you have seen it here, you can add every if we take a reference of like a reference means we are directly changing at that particular address, and if we do that we can add any number, so addition is pretty similar. No matter if I like instead of a plus plus I do a plus 5, it will work the same way. Like just for showing you guys. So see 5 and 10, so it added 5, so it's basically we are directly going to that address, changing that, and like then that's why the actual value is getting changed. Now let's see what happens if I do ptr equals ptr plus 1. Now as I have told you before, ptr basically stores the address of a place, okay, and it's of type int. So what will happen if I increase ptr by 1? Basically what happens is that as the like as it knows that the heap memory it's of type int and every point will take 4, so what it basically does is that it takes ptr not to the immediately one. Like suppose say these are two consecutive, okay, and if it's say 100, doing plus 1 to this won't take this to uh, 101. Why? Because here every int is taking 4 bytes. So basically, where the next contiguous location will be at 104, 104. Sorry, yeah, and that's how like the pointer propagates forward. And I will show you guys how its real life implementation have been made in different data structures. So yeah, here ptr equals ptr plus 1. Let's print it once. I'll be providing the whole code with comments in GitHub, so you guys like if you want you can just you don't need to follow along with code. Okay, ptr. Let's just print ptr 98. See 94 it was previously. I hope you guys are understanding. It was 94. It increased by 4. It's 98 now. So basically, the 4 in contiguous location bytes taken by the int data type has been skipped, and we have moved to the next location. So yeah, that's all the like preliminary concepts. Now we'll be learning about how pointers works with arrays. Okay, let's say I write. Let's comment out this part. I might repeat variable names. So if I write int arr, say a number like 10, okay, and here I say any 1, 2, 3, 4, 5. Okay, now you guys are what happens? Why is it giving error? Okay, semicolon. Okay, so you guys are now familiar with the thing that if I what will happen if I print arr 0, it will basically print the first term, second term, third term, and so on. But what will happen? Have you ever wondered what will happen if I print arr here, just arr, no indexing and stuff? Let's see. If I print arr here, it gives me a location. So what is this location of? Like now, basically this array contains many integers as you can see. So what do you think will be the like the location of the arr, like this location? So basically it follows the same like same concept as any other data types. Like I have told you int, what it does is that if it has a long like chain of, for here we have 10 different elements in an array, so what's the size of this? The size of it, this is typically, if you take the whole size of the array, it's typically, now it's taking 4, but the whole, it will take 10 into 4, 40 bytes, and every element will take bunch of 4 bytes, 4 bytes. So what typically happens is here is that arr stores the first byte, because then it will easily be able to like communicate and propagate like to the following addresses by just doing +1 +1 stuff. Okay, I will show you now. If I Similarly, so what we understood now is that what ARR printed is basically the location of the first index of the array. Let's check it out. Yeah. Okay. See, it was basically storing the first index of the array. Okay. Now, you guys have like I previously told you that array is a contiguous memory location, and also what happens is that uh, doing plus one with any address makes us takes to the next accessible address, not to the immediately next bit. Okay. So just from the intuition I just gave you, I'll be looking into the chat for a while. What will ARR plus one take us to? Just throw any random guess or stuff. Where will ARR plus one take us? Considering that ARR is a contiguous memory location and ARR points to the zeroth index, where will ARR plus one take us to? Any guess? Any wild guess? Okay, like no. Uh, okay, sure. I'll go ahead with the explanation. So as I told, heap memory has a typical tendency of storing data in a contiguous manner. So we have a typically presently we have four. So I'll be making boxes here because I'm not that good with drawing lines. So yeah, let's consider this as so we what we just got was that here let's say a0 was the this one. Okay, and a1 is this one. So what we just learned previously was that in case of contiguous memory location, and when the data type is already mentioned, it skips to the next location. So accordingly, we if we think from that perspective, a arr points at this one, like this thing. And if we do plus one, theoretically it should take us here, because it's basically the contiguous next location. Let's see if it does that or not. So if I just print C out, let's ARR plus one and ampersand ARR one. Let's see if it's same or not. Run code. See, it's taking the same, like it's basically the same. So from this perspective, you can say that ARR plus one takes us to the location of ARR plus. So like it's basic intuition that ARR plus I, where should it take us? It should take us to ARRI. Let's check it out. Say any random number, say 2. So if I do ARR plus 2, it's the address. So how to get the value? Ampersand. We need to dereference the thing. For visibility purpose, I'll be adding some space. And if I do ARR 2, let's see if it's same or not. 3 and 3. It's the same. And you guys will be surprised to know that this is how exactly arrays work. I could have implemented, but we are running in short of time. So and ARR so we get to know that these two things are basically the same. And if you guys have any problem understanding this, what we basically are doing is that we are moving to the next location, that's the second index, and we are dereferencing it. We are going to the value of it. That's basically ARR2. Okay. If you have any doubt, you can write in the chat, and please, who are the moderators, please let me know if someone is writing any doubt. And yeah, like this thing pretty much works the same way. Okay, I will be in a fast and this thing works the same. And this brings us to an interesting concept that we are saying, what we are saying is that star ARR plus I equals ARRI. Okay, this is what we are talking about. So from this point of view, ARR and I are commutable, right? Like it doesn't matter if I write I plus ARR or ARR plus I, because they are the same. We are just adding two things up. So going from that point of view, wouldn't wouldn't I ARR of I equals I of ARR? Isn't that the same? Let's find out. So we'll be doing, let's take a variable, random variable, int I equals 3. 2 we have done on 4, let's 4, and I do ARR of I and I of ARR. Okay, let's see if it's same or not. It's the same. I have like forgot to add the, but you get the concept. Basically this is how exactly how arrays work. If I get some time, or in the next session I will or try to show you guys how arrays work in the hindsight. And now we are almost done with the pointers part. Just one more thing. uh, let's comment this out. You have typically seen that if I say int num equals 5 and I pass it to a function, let's say mul2, it's just a function that multiplies it with 2, and I say here num. Okay, and here what I do is that now here I'll be creating a function. What was the name? And if I make the value of num twice here, okay, so what's this error? Normal equals, I might be missing out on something, but can you guys please point it out? Like I'm coding, so I might be missing out on something. Why is this error coming? Okay, we'll find it out. If I just say no, the value of num should be printed. Hey, anyone, like, can you please point it out? Like, I might be making some mistakes or stuff. Let's leave it. Let's just print it out. I'll be printing once here also, just to make sure that here the value increased. Okay, let's give some space here, and I'll print this. So yeah, the value increased here, but it's the same here. It's basically the same story of shallow copy. The individual like what happened is that typically for this kind of stuffs, a stack memory is created, a stack memory, which like as previous session is on stack. So a stack memory is created, and when you, okay, let's not create this. When suppose there's a the main memory here, and when typically you create a function, it goes into another stack memory, and the if the function has a return type, it typically has a responsibility to return any value, but it's a void type. So here it has a num, it takes a shallow copy, it just takes the value here. Okay, it multiplies it by 2, but there's no like, it has no reference to each other, so the value doesn't get changed. Now at the same time, if what I will do here is that if I send the address here and receive it with a pointer. Okay, and here I increase the pointer's value. Sorry, call is, yeah, sorry for that. So, and typically I increase the pointer's value, that's the same value of num by 2. Let's see what happens now. Wait, okay, sorry, it should be star num because see both the values have changed, and because I am sending the address here. Let's see like a quickly that what happened here. So let's say it's the stack space, consider this is above this one, okay, like a stack. What happened is that from here we sent the address, like suppose say it was 500, we send the address here, like take the address from here, it like it told this one, refer to that. So from here the stack created it referred again to here and increase its value by 1. So here it increased its value by into 2. It did it into 2, like the value of this, not 500 into 2, the value of 500 into 2, basically it sent the address, it received the address, it's pointed towards the location, that what's the value, like value at 500. It got to know that it's 5. Made its value twice, which is 10, and like it didn't return anything because it has type void, and after that the value of both the thing increased, like went twice. So yeah, that's everything about pointers. If you guys have any doubts, you can just write in chat if you have any doubts regarding pointers. Any doubts? Okay, I'm assuming every one of you have understood the whole concept about pointers. So we'll start with the linked list. So to start with linked list, let's first understand what was the problem with arrays. Now let's consider we declare an array of size 10. Okay. So as you know, array is contiguous memory location. And let's say you are building an application of stuff and there are multiple arrays. Okay. Now a server is not infinite, as you know. It's a single computer where the program runs. So let's say you have already like declared many things. Okay. One is here, one is here, one is here. Okay. And let's say for like cumulatively and contiguously space left is say 8 9, and you need a array of size 10. Okay, just saying it's not a real life scenario, but why it was like where this intuition came from. So basically the contiguous space is less than 10, so it will create a problem if you declare an array, or it will not let you. But actually if you think about it, the fragmented space present here is a lot more than what you want. Okay, so basically if you just consider like contiguous spaces like this, it's not a very like the approach can be improved and it can be modified to like to satisfy our requirements. Okay, so what the developers came up with was addresses in a contiguous memory location, and this can be increased and decreased to like still there is space in the heap memory. Okay, now in this way the location can, and also there is no fixed location. If your array only needs space 2 and the previously needed like 3 spaces are not needed, where there will be two
flexibility read it from 3 to
individual
2,
and there is
uh,
no like
say,
problem with that. So
say
you might be
interesting
thinking
like
that we'll
what
be
I
using an array
did,
and stuff,
and
but typically what they use
access the values
is
present
that
here. Okay,
like we'll be using object oriented programming here to address this and to make it like a custom class to say it. Because you all of you guys might not be familiar with classes and stuff. So what the thought was that they'll be making a custom data type, and in typically in C++ or any other object oriented programming language, classes can be used to create this kind of stuff. So let's make a different file here. SLL. It means single linked list. Single linked list. CPP. Okay. Now what I'll be writing here is that this first code is just the same. Okay. And here, oh no, it's using names. Okay. Now they thought that they will be naming each of these total default data types as nodes. You can name it anything, it doesn't matter, it's just the approach followed till now. So I'll be making a class node. If you don't know about oops, don't worry, I'll be showing you about the basics of how this thing works. Now what we do here is that it typically classes are made to, like, there are, like, suppose say there are many attributes, or what to say, or parts of a thing. Okay, like say a car covers many things: a steering wheel, a clutch, a brake. But if you think of it or see it from the outside, it's just a car. Like, so a class is just a covering of a whole thing that represents all the internal parts and stuff. So here it also gives you the the option to make things private or public. Private means it's just accessible within the class, or else it's not accessible within the class. I will keep the classes thing minimal today because I don't want to go deeper into it. It's a completely different topic. But for now, if you want to make things of a class, let's suppose think of it as a house. If I want to make the things like things present within a class to be accessible from the outside, I need to make it public. It's a keyword to make things accessible from the outside. Now typically, as you saw here, there are two things. One thing that will hold the data of this, so let's write it int data. And another thing that will point to the next node. Okay. And it will be of, now what will be the type of, let's see. As we have discussed before, the type of the thing that's pointing is basically what thing it's pointing to. I am pointing to a car. So basically, if I'm a pointer and I'm pointing towards a car, then my type should be of a car. That's how pointers work. So typically the pointer will be of type of the type we created, that's node. So we create here a type known as node star, and the address that will be storing to be in a variable name next. Okay. Now this basically constitutes the part of a node, single node. As I told, the node will have two parts: a data part and the next part that will be pointing to the next part. Okay. Now every class has a constructor. What a constructor means is that, suppose say, uh, from the I will be talking about it from the program point of view. So if I say, if the user declares the data blankly, what should be the default values or the initial values coming to it? Okay. Now here, every time I have seen a linked list of stuff, when the data is declared, it's typically declared with a value. So a value will be a must. And and the other things, such as what will be the next node and stuff, can be manipulated later. The present value can also be manipulated, but it's always given in beginning. So I'll be giving a, like, it will be accepting just like a normal function. It will be accepting value like int val, and it's also will be accepting the address of the next thing as a pointer. Okay. So it will be node star, let's say next one, next one. Okay. And what will be happening here, basically, you guys will know, like, get to understand it better after you create and use this stuff. So here I will, like, initialize the parameters of my class with the user given value. Okay. So data equals value. Okay. And next equals next one. Okay. So the user gave two values, and I initialize those two values with the attributes of my class. Now you'll get to see how this thing works. I'll be declaring my main function. Okay. So to typically declare a class, or to create a class of stuff, what we do is that we will be writing here node Yeah, let's start from here only. And another thing, typically as we have seen here, like in every linked list, one node points to the next node, and similar to the one node points to the next node. Here the first node is known as the head node, and the last node is known as the tail node. So here the first node I'll be declaring is head. Okay, so here I declare head, and like let's give it a name, any like any name you can give it. So oh no, so I'll be declaring a head, and how to declare is that new node. Okay, and here we can pass two values. Okay, now let's say I am trying to create a node of a value 1. It's the head of the linked list. Okay, wait, what happened? Okay, so basically what it's telling us, it should have accept two parameters. So for that I'll be making just it will be, I'll giving here a ptr null pointer, because if it accepts one value it will assign a default value to it. And it basically means nothing. It says that if the user does haven't provided this parameter, then you just default it to the null pointer. Now you might be wondering what's a null pointer. For cpp, instead of using null for pointers we use null pointer. Okay, so now we have declared a like head, and what I will do is that I'll be declaring another similar node known as the, suppose say head 1. Okay, and I'll be giving it a value 2. Okay, now as I typically said, you can make pointers point to the next thing. And how to do it? To do it, what we need to do is that head, this is how like you point access the parameters of a class when it's typically using a pointer. And if I say next, okay, equals head 1, and let's make another one, head 2. Okay, 3, and head 1, and I'm pointing head 1 next to head 2. Yes, it's correct, I hope. Now what we just did, let's see what we just did. What we basically did here is that we created three different nodes. Now each node will be having a data type part, like this, like this. Okay, I'm not doing for the third one. It's head 1, it's head 2, and this one's head 3. Okay, now let's assign some addresses here. 100, 550. I'm just assuming values, it's not. Oops, 600. Okay, just like that. So from this point you should be clear about the thing that the value here that should be pointing here should be 550. The value present here should be pointing here, so it should be 600. Okay, and now present here are the values that I have assigned a value 1 here, a value 2 here, and a value 3 here. Now its next will be empty, and or to say null pointer, it will be holding a null pointer. Okay, and as I told before, this will be pointing to each other like a train, like I just like to say like a queue or something like that. Okay, now what we basically did is that we created nodes individually and make all of them joined by doing this thing, what that we did here. Head next, the next part of head points to head 1, that's this one. Okay, like head 1, head 2, just replace it, it's just different nomenclature. And head 1 next points to head 2. Okay, now how to see, like let's make a function that will traverse the linked list. Okay, let's create a void function traverse ll. Okay, what will accept? It will accept the head. Okay, and what it does is that now you will see that, like doing next next next, you can like go till the end, well, while there is no next, like when it becomes a null pointer then there's no next, right? But you will see another thing, that if I start iterating through the head, then the head, like let's say it's the head, if I say head 1 equals head 1 next, so head 1 becomes head 1 next, so it comes here and it becomes this one. So now we have no access to head anymore. And as in linked list, singly linked list, we cannot go to the previous, like back, so we won't be able to access this one anymore. And it's a serious problem in linked list because the memory created in heap is typically permanent. Okay, and this cannot be like it needs to be manually deleted. It's not deleted like what to say automatically in C++, whereas in if you are using Java, there's a in Java clears it automatically using a garbage collector. Okay, so what I'll be doing is here is that to like keep the head unaltered, I'll be creating another pointer. And as I saw how to copy a pointer, note start temp equals head. What do my iteration criteria needs to be? If you think of it as a while there's a valid data present, while iteration. So basically while temp not equals null. Okay, null pointer. Okay, I can go temp equals temp next, right? Like this. Temp equals temp next. Okay. Um, I'll need to print it here because I want to see how the traversal is working. Temp. Now I need to print the data of temp, right? And you know that the data attribute of a variable is stored in temp data. Okay. So I'll be printing it. No, on it. And after this, I'll be giving a handle. Okay, what I basically did was that I made a function which will iterate through it till it's the end. Okay, and you know that I don't need to give it. It can be same if I give temp while temp is valid. Just print it. Okay. So and what I'll be giving here is that I'll be calling the function traverse ll, and I'll be passing the head here because head is the point from where the traversal needs to start. And I'll print it. Let's see what happens. Hope it's not error. So yeah, it printed 1 2 3. Okay, and in the similar way, if I print it in a different manner, let's say if I print instead of this, let's comment out this line, and if I print temp data, no, let's not do this. It will give yeah. So basically what it did was that you can see it went through the whole thing. So in this iteration what we basically did was that we created a temp variable here, okay, which was pointing here, and from here we do it temp while temp is valid. Okay, now if I minimize this thing, here it will be pointing towards a, as you can see, a null pointer, right? It's a null. So what basically temp did was that it went here, yeah, temp is valid, went here, temp is valid, still temp is valid, but when it went here temp is no more valid, right? So that's how it occurred, and at every step we like printed the value, so 1 2 and 3. So yeah, that's basically what it does. And there's another way of doing this where what we do is that Like instead of using the arrow is typically needed when you create a like you might be wondering, you can also call it like a normal. I will show you guys. This can also be done like node star head equals just node. Okay, like so one. Okay, now it's okay. Yes. Okay, so what we did was that we just created a function of the type node. Okay, we just call this function and created an object. Now here, instead of using the array thing, what you do in this typical thing is that we do head dot data and next. As you can see, the both the values are available. One will be printing a null pointer and one will be. Let's just print the data. No need to print this one. You guys now might be familiar with this thing. So if I print this one, as I thought. Now, what's the difference between these two types of initializing? So when you use the new keyword, okay, let's say it's a heap and it's just a stack memory. And just to say, the stack memory is a temporary memory which depends and gets created and deleted based on the scope. Now, what does scope mean? Scope means till the data, till the part the variable is accessible. Let's say I have a function. Okay, let's say I have a function like I'm just naming it like that, function A. Okay, here I declare num. Okay, as soon as the function A ends this part. Okay, it's accept some value. Okay, I'm just doing this one for the understanding point of view. So this the scope of this thing num is only inside this function. So outside this, num has like no existence. Okay, so in stack memory, what happens is that there's a main function stack. Above it, it has a function stack for here. Now here it declares the memory and doing stuff. Whenever this the a is the a returns a value or whatever a does, a is a void function, it work is done, this typically gets popped out and these things get like this thing gets deleted. Okay, how to select this? Yeah, these things get deleted, so the data stored there was totally temporary. Okay, it wasn't permanent. So but this was for if we use the object type, the thing that I just showed now, without using the new operator. But if you use the new operator, the data created is in the hash memory, heap memory, sorry, what I'm telling, a heap memory, and the data is permanent. So this needed to be cleared like by us using the delete keyword. Okay, I'll be showing you guys that. Now we won't be going with this kind of notation as it's not typically used. I'll be showing you what is used today nowadays. So let's start with something. At first, I will be let's create a array. Will be at first we'll be what we'll be doing is that we'll be creating an array. Like we'll be initializing an array. Let's say let arr 10. Okay, equals it's the same thing 1 2 3 4. Okay, and we will be making a function that will convert the whole array the whole array to a linked list. Okay, so let's start with the intuition first. We'll be coding that later. Let's say we have an array. Okay, 1 2 3 4. Okay, 5. So what we need to do, the whole algorithm or the step by step process will be going through is that at first, let's say we create a head. Okay, we create a head. I will not be writing the whole stuff because it will be taking time, and it has a value 1 here. Okay, now this value 1 will be making this, and typically will be initializing a variable. Let's say previous or prev. Okay, I will get to know while I'm naming it like this. Prev here. Okay, prev. How to increase the size of letters? Yeah. So it's typically named prev. Okay. Now what we'll be doing is that um, see. inside the function, let's say convert array to linked list. Okay, we will be accepting nothing but the array. Okay, wait. Okay, we'll be accepting the array here and also the size of the array. Okay, so let's close things as well. Now, what typically will happen here is that inside this we will make like we need to make a head to be the point of contact with the first thing. So ARR of 0, and like there are some edge cases that you need to consider, like if size equals 0, return null pointer. These are basic stuff. I won't be covering this anymore. So at first, what we do is that we make a like the first thing. Okay. So what happens here is the first thing is made. It's named temp. Okay. Sorry, head. And then what we'll be doing here is that will be making another pointer named prev, that will be pointing to the head. So as I told you here, that there will be two things pointing towards the head. Okay, now it's understandable from from the point that array can be of very big, right? And we should not do it manually. It shouldn't be done manually. So we'll be moving towards the iterative approach. So what we'll be doing here is that in the similar way we will move ptr no, while prev, yeah, while prev, it's okay. Hmm. While pref, let's not do this like this. Let's, as we have to iterate through the size here, for and I equals 1, let's say I should be less than the size of the variable here, and I plus plus. Okay, so what we will be doing here is that, understand, here after going, you know that, as like I took okay, so why I took 1 here, because 1 0 I have already initialized, it's already made. Okay, so what I basically need to do here is that here it will be pointing towards another, let's say it needs to be like this, right? So what I will do here is that inside this function, after I move into this function, I am into a new I, the value of I is different. I'll be making the node for the new ith variable. Node start temp equals new node. Okay. And what will be the value of new node? ARR I. It's pretty self-explanatory. I'll not be explaining this. And after that, you know that temp has been made. Okay. Temp has been made. Temp is this one, which is holding the value 2. Okay. Now you know that the link is not yet present. This thing is not yet present here. So what we need to do? We need to make this thing point to this thing. So here we'll be using the here we will be using the temp prev variable. Okay, and we need to make prev point towards okay, no, wait, we need to make prev point towards the present variable, that is temp. So basically what happened is that this thing, we made this thing point towards here. Okay, prev prev, what am I writing, prev next equals temp. Okay, so the previous variable started pointing here, and as we know, during the iteration, if we, in the next step we'll be going and making it point towards another whole new variable, right? So if we keep prev the same, then this thing will not be there. The thing that will be there is that something like this points to this points to this. It's not at all right. It's not at all right. So what we need to do is that we also need to take prev to the next thing, that's a temp. Okay, so we'll be writing here prev equals temp. Okay, now that's all the thing that we need to do inside the iteration part. And what we'll be doing here is that we'll be returning the head. We'll be returning the head from here, returning the return return the head from here. So this is the function, and I think you guys have got the intuition of this thing part. I'll be adding the this thing into the code here. Okay, so yeah, there will be some typos and stuff. That's not an issue. Node star. Okay, yeah, it's okay. Now from here we'll be determining the size of this thing, which is basically int size equals size of ARR by of ARR 0. Hmm. So yeah, it's a semicolon. And here we'll be calling, okay, node star head. We need to we'll be receiving the head from, like, we'll be getting the head pointer from here. So value of type int cannot be initialized. What have I done here? Okay, it will be returning the convert to AL function. Here the thing that will be going is that the ARR and the size. Okay, now after this I'll be iterating over the head once again. Okay, and let's comment out this part. It's no more necessary. Let's see if it works. I hope it will. 1 2 3 4. It's basically 0 0 0 0 because like I haven't initialized the next variables yet. Okay, and I have, like, here I have done this thing here. So but you can see that the 1 2 3 4 part that I just initialized is it's working properly, and like there's no issue here. Now what I'll be doing here is that let's not take let's take some extra, let's make it of size 4, or else it will be like problem. Yeah, so now it's working properly, as you can see. I hope the like this part of the code is clear to you all. Now we'll be moving towards the insertion of values and stuff inside the linked list. So yeah, let's make another function, insert head. Okay, in this function what we'll basically do is that we'll be inserting data, like in the we'll be replacing the head, and we'll be inserting a like a different uh, uh, what to say, like a different head here. I will be showing you guys. Here the function will receive a head, the same, oh, sorry, it will be node, the same thing. Okay, it will be receiving it I will initialize the function node star node star insert head. Okay, now what we need to do, it will also receive a value, because what will be the value of the new head? Okay, for that it will receive a value. Okay, and let's say the value it will get is 0, because we already have one, I guess. Yes, we already have one. And yeah, the head here will be received because the head will change now, right? So the same edge case, some edge cases you need to handle. If there is no head, just return a null pointer. Okay, if there's no head, just return a null pointer. Now it we need to create the new, like the new variable that will be the head. So let's name it temp, because it's a temporary new node, and we'll be naming it value. The value it will contain is value, And what else do we need to do? The other thing that we need to do is that temp, the variable should point towards the head, right? And then we'll be returning the temp from here, because the temp, like, let's see what just happened here. Okay, now there was an existing linked list and I needed to insert a new linked list. Okay, insert a new node at the beginning. So what I did was that at first I created a new node, temp. Okay, and create a new node temp, which I gave a value which was 0. I gave here the value 0, but it's still not connected, right? So what I need to do is that I need to make this thing point here. Okay, so temp next equals head. This was the previous head, and you can do the thing that head equals temp then return the temp, but it's basically the same thing because it's just a function. So if I return temp from here, as I'll be accepting it here as the head, so it's inserted now. And yeah, I'll be traversing the linked list again to see that whether 0 has properly been inserted or not. See, 0 has been inserted. Let's not print it like this, let's print it like this only. Okay, it will be easier to visualize the thing. See, it was 1 2 3 4 previously, now it's 0 1 2 3 4 because I just inserted 0 here. Okay, now similarly you can also insert at the tail, like at the end. It's here we don't need to change, the head will not be changed in insert tail. Okay, let's first visualize this thing again. So what we'll be doing now, we'll be inserting at the last. Okay, like at here. So what I need to do here is that, let's analyze the steps. At first I need to create a new variable. At this temporary I will name it temp. I need to give it a value. The value will be given by the user, let's say 100, it can be anything. Now it needs to be the adjacent, like the next node of the which is connected to the last node, right? So what we need to do is that we need the last node to point towards this node, right? It should not be a null pointer anymore that it's pointing at. So the steps need to be follow is that at first we need to iterate all the steps, go to the last node, create this node, make this point to here. Okay, that's what we need to do. So let's code it up. Let's create a new function. Let's create the function first. It will be a void type only because the head will not be altered. So let's not return a head now. Insert tail. Okay. From here, I will be receiving the value node star head as usual, and also the value because I need to know which value will be inserted. So I will be taking these two values from here. The similar thing, I'll be just copy pasting this thing. If there's no head, just return this value. Now, okay, it's a void function, just return. Okay. Now from this point of view, as usual, I'll be need to iterate, and we cannot alter the head because then the previous nodes become unapproachable, right? And as you know, I will show you guys why approaching those nodes is, it's also like properly like understandable why we need to. So node start temp equals head. Okay. Now I need to go to the like the very last. Now you might say that while temp equals temp next, this thing, right? And as usual, you know that I need to make a new node, right? So I can write temp next equals a new node will be made that will have the value of the given value. Okay, so this is the basically the code. You might be thinking, yeah, this is right, but there's a catch. Let's visualize this from here. Here what I'm doing is that now we have the updated one where the temp is here. From temp you are going here, temp is valid, temp is valid, temp is valid, temp valid, temp valid. Next it goes out of bound, it becomes a null pointer, and then the temp is invalid. Okay, Now if temp is invalid and we have reached temp, taken temp there, then in linked list we can in no means we can go back here if it's a single linked list. So we cannot make temp go to the null point. We need to make it stop before it reaches the null, right? So there should be a small change. What we'll do here is that temp next is null. Now what it does, instead of checking at every position that let's say this, it checks that temp next is null or not. It checks temp null, it's present, yes it's present. Temp null, yes it's present. Temp null is, yes it's present. Temp null present. Temp null no more present. So it stops here, it stops at the last node. Okay, now that's beneficial because then after that we'll be assigning a new node at the end. And yeah, it's basically that. The new value that we'll be assigning is, okay, let's insert a value once more. Okay, it's already 9:34. It will be taking a bit more. Please bear with me. I'll be covering the single English today. So as usual, we'll be passing on the head, and also we need to pass on a value. It's still 4. Let's pass 5 for the better understanding. And as usual, we'll be traversing and printing this thing because that helps in the visualizing purpose. Okay. So see, as expected, 5 is inserted, which is the last variable at the tail. Okay, like any doubt from anyone? You guys can write doubt. Like it's okay. It's not a very easy topic to start. We also had problem understanding it in the beginning. So yeah. So now what to do? Yeah, we have inserted at the head, inserted the tail. Now let's understand, if we want to, let's say the user wants to insert a node at the point, like say the third index. Okay, what to do? Let's again move here. Let's make a fresh one. It's already cluttered there. Okay, let's say, yeah, it's the linked list. Bear with the diagrams I make, as it's just for the understanding purpose. So yeah, so let's say I want to insert a node at the third position, first, second, third. It's basically the third position. I want to insert a node here. Here, okay. So what should the algorithm that I follow? Now you know that to insert node in the third position, considering this is the first one, this is the second one, okay, and this is the third one. So as usual, we cannot iterate with the head. So we will be taking a temp here. Okay, the temp variable here. The temp is here. And if we think about it, we will need to iterate till 3. If we iterate till 3, you think we are already at the third position. And anything you can insert here. But it will be getting inserted at the fourth position. So where's the last point till which we can iterate? For here, like the last position where I'll be iterating is 2, because 2, from 2 the next variable is like approachable, and we'll be able to make a variable here. So what we'll be doing here is that first we'll be making a variable temp. We'll be making temp to, taking temp to 2. Okay, we are done with the iteration part. Now what to do? Now what we have to do is that we'll be making a new variable, like a new node here. Okay, the node here is created. Now you know that if the new node is a part, we need to make it a part of the linked list, right? So what we need to do, basically we need to make this thing point here, this thing point here, right? So two joints need to be created, one joint needs to be broken. Okay, from this point of view. So I think it's pretty clear. We'll be creating a node, we'll be making temp next equals new node. Okay, new node next equals this one. Okay, so the new points will be created and deleted respectively without harming the existing structure of the linked list. Okay, now let's code it. Now here, considering that the user might give the position to insert the head as 1, so we'll be like then the head will be altered, right? So we need to return the head from here if the head is altered. So head equals, let's name it insert at position k. Okay, so head, what will receive next? A value. So let's say we'll be giving the value 100. Okay, and the position we need the value to be is at 3. So let's make the function now. Okay, and the second parameter was, I guess, inside of, yes, okay. Second parameter was the int value, and the third position was, it was the um, position, or let's say k as I named it. So what should be the first thing we need to check? As usual, if not head, return null pointer, because here it's expecting a null pointer. It's expecting a return value. Okay. Now you might think of another edge case. Like here, if the user gives the value 100, we only have 5 elements, 6 elements. So how can 100 be approachable? So here, if okay, so if the thing we need to check is that if the size of linked list, okay, plus one, because the new value can be added the last, right, is less than what the user wants. Okay, like the, then it's not like it's not a, like the user is not giving any proper values. So then we should return a null pointer again. Now this function doesn't exist, so we have to make it. It's basically very simple. I will be just copying from here. But where's the traversaler? Yes, traversaler. So size of, okay, see, it receives the head. It will be c equals 0, counter variable. Instead of printing this thing, I'll do C++. So at every iteration, the value of C will increase, and I'll be returning C from here. Okay, it's pretty like self-understandable. I'm not explaining this now. Why is okay? Okay. So basically, it will return the value. Sorry for being late. Like it will take 10, but I hope you guys are understanding. So yes, I just iterated to every pointer and increase the value if the value is present. So now I am getting the size of the pointer, and if it's exceeding the present length plus one value, then there's no sense, because I'll be showing you the the size that will be increased will be plus one, right? So if it's more than the plus one of the present size, then it's like not a feasible index to be inserted at. Now there's another edge case. If the k is 1, then just pass it to our existing function insert head, okay? Because that's basically what the insert head does. We are done with all the edge cases now, okay? Okay, there needs to be a value. Yeah, yes. Now we have dealt with all the edge cases. Now we need to do the operation that we just saw in the whiteboard escalator. We'll be declaring a temp variable here that will be pointing towards the head. Okay. Now here, as we just saw, that we need to go here. Okay, and we need to point it here. Okay. So basically, what you can basically do is that you can run a for loop. Okay, one, sorry, I less than k, I plus plus. Okay, and here temp equals temp next. As I am giving less than k, so it will be going to the, like the previous position, And yes, so now I am assuming, and yes, not assuming, it's done that the temp is presently at the variable before the place, like the second variable if I want to insert at the third place. Okay, it's already present there. Now what I need to do is that temp is pointing towards the variable that should be like temp here is pointing here, right? But if I break this bond, okay, let's say temp next equals this one, okay, then I have no more contact to this one. How will I go there and make the changes? So you need to be careful about this. So what I will do is that I have first I will be creating a new node. Okay, node star new node equals new node, and it will be having a value. Okay, I created a new node. Okay, with the value. Now to avoid from being like losing contact from any of the nodes, at first I need to make, because see, if I make temp point here, this bond will break. Now I have no, now presently if I see, I also have no access over this, right? New node is made. If I make this point go from here to here, it's totally separated. How will I access this? So you need to keep this in mind. So what we need to do is that at first the new node needs to point here. So what should be the thing? New node next equals temp next. Okay, so we made it point here. Now what we can do is that now this is approachable and temp is also here, so there's no fear that we'll be losing this part. So now we can make temp point here. Okay, okay, temp next equals to new node, and yeah, everything else remains the same, and we'll be returning the head because we are returning a head here, and as usual we'll be traversing the linked list again. Let's see 100 is inserted at the right place as we expected. 0 1 2 3, it's inserted here. Okay, now we have inserted the linked list at any doubts till now? Hello, no doubt from anyone? Okay, sure, I'll be assuming that all like you guys are understanding everything. So yeah, now I'll be moving towards the deletion part. So what we need to do to delete the head? Now, as you need to know here, we have to keep in mind whenever we are altering things, because we can lose point of contact to the nodes and stuff. So let's say we have a linked list with three nodes. Okay, let's say three nodes. If we need to delete the head, you might be thinking that's the fear we are having. So let's just not think about it and move the head from here to here. We are done, right? You cannot go back. The head will iterate only front. So what's the big deal? Now I told you one thing previously, that the nodes or anything that is created using the new keyword is added to the heap memory. So it's needed to be cleared manually, right? So we cannot lose point of contact to this one. So we will need, what we'll do is that we will make temp variable point here, make head go from here to here. So it's basically just, head equals head next. Okay, head went to the next one. Now head is here. This one is not approachable from head. But yeah, to clear up the memory, we'll write delete temp. Okay, so let's code it up. Delete, delete head. Okay, let's code the function. Here we need to return the head because the head is already obviously getting altered. Okay, Delete head, it will accept the node star head, and no value because we are deleting stuff. So if no head, you know what to do, return a null pointer. Okay, now what we can directly do is that, okay, there is a typo here. What we will be doing here is that, so there's another edge case. If head next is null, then what will happen is that no linked list will no more exist because there's no more element left, right? So then also we need to return a null pointer. These are the small edge cases that you need to keep in mind. Now, as you know, I before moving head forward, we'll need to create denote start temp equals head. I initialized a variable, then I moved head to the next position. Head equals head next. Okay, head equals head next. Now I will be deleting temp. I will be returning head. Okay. Note delete head. It will return a new head. So we need to accept it. Let's see the head is properly deleted or not. 0 is deleted, you can see, so the head is properly deleted. So yeah, it's already 9:50. Bear with me for a while. I'll be covering two more functions, delete tell, and similarly let's visualize it again. I want to make you guys understand it visually so that you can implement new questions along with it, not just the questions I'm like just the things I'm doing here. We'll also be having a session tomorrow where I will be discussing about one more type of linked list and different lead code questions. So yeah, let's say we have three, and as usual, we know that what we need to delete is this one. Basically, this one needs to be removed. So where we need to go? We need to, as usual, we cannot iterate with the head. Make a temp here. Make the temp go here, because if we go here and we just delete this, who will delete this reference? There is a reference here, right? There's a reference that pointing here still. So if it's not like present, it will create an error. So we need to go here. Okay. Now you might be thinking then how to delete it. So for this, we'll typically be needing uh, two different uh, two different variables here. I'll be showing you guys by just coding this thing. Uh, there's actually no need to return ahead. Okay, as usual, it will be written. The first point remains the same, so I'll not be typing that anymore. Now, note. Okay. Yes. So now, as you have seen, if I go to the last point, I cannot remove this reference, right? So I need to like remove this as well as remove the reference. So where I will need to go is here, this place. So how to go here, right? There's one thing that we can do is that we'll be taking two variables, and every time this will be propagating one time slower. So we'll be doing nothing, just uh, one approach. What can be one approach? I will be showing you guys. Let's say we'll take another variable, node star pref. Okay, head. So while temp next. Okay, um, pref equals temp equals temp next. Okay, so what am I basically doing is that see, there's two variable temp and prev. Okay. So at in first iteration, say I take the prev equals temp. So prev remains here, temp moves here. Okay. Uh, Now in the next iteration, prev moves here, prev equals temp. Okay. Now temp equals temp next. Temp moves here. Now you know that our condition is temp next should not be null. It's, if you see it once more, temp next should not be null, right? So yeah, temp next here should not be null. So what you can basically do is that temp next should not be null, temp will stop here, but prev will stop here because prev is slowly incrementing, like it's not updated at the last, so it's not like it's basically uh, like it's pretty intuitive. You should like, yeah, it's pretty intuitive. And as temp stops here because there's no more next, so prev starts here because it like it stops before the last iteration happens. So yeah, like this you can do it, but there's a better approach. I can say temp next next. Okay, while temp next is valid, let's iterate temp. Okay, so in this way, temp is known not like not anymore needed to be, like we don't need any two variables anymore. Okay, now temp next equals null pointer. Okay, there's nothing to be returned and the bond is broken. But yeah, I just realized that we will be needing another thing because the temp present at the last. Okay, let's go back. Let's understand why like needed to redo this thing, because prev is present here, like prev is present at the second last point 4. So if I say prev next equals null pointer, I don't have access to this anymore, right? So I'll be needing access to temp. So temp, because we need to delete temp. Yeah, it's done. Delete. Okay, it's done. So I'll be using this again. Okay, we'll be passing the head. Let's see if it works. It should work, hopefully. Okay, last two got deleted somehow. Okay, let's debug it together. So what happened? Temp was update. Okay, I forgot to change. Yeah, yeah, understand. You guys need to like play with pointers and stuff. Then we'll get to know it's like how it's see. Now I went to the last position. The last position went to temp. 4 was prev. Prev removed the next pointer. 5 was removed. 5 was deleted via delete temp. Okay. Now only one function is left, that we have to delete the element at the position k, as the same we did for the first one. Yeah, here also the head can be deleted. Let's not delete the head anymore. Let's delete just, I'll be naming it similarly. Delete at position k, I'll be giving the head and also the position that I need to delete. Let's say it's 2. Okay. And as usual, I am doing it now only. I'll be traversing it and printing it. Now let's create the function. Void. Okay. Okay. I won't be repeating this again. So yeah. What are the other edge cases you need to see? Okay, let's understand delete at position k. Okay. So let's say it's the same thing. Let's say it's eraser. Let's say I need to delete the third element. So the element, uh, the second element. Okay, this one I need to delete. So what I need to do, as it's pretty understandable now that the temp, the variable I need to access is this one. Okay, and if you basically think temp, what's the change that we need to do if you delete the perspective that you need to, like, if, forget about this one, if I just write temp next equals temp next next. Okay, what happened? Temp next is a variable that's, let's say it's pointing here blank. What's temp next? Okay, it's actually pointing here prep, but just for show, temp next is, temp next is here, right? So it's basically what it's doing is that it removing prep from accessibility, so it will not fall under the iteration, so it's basically deleted. But as we know in point, like typically in this type of where we are declaring with new, we need to like manually delete it. So what we'll be doing is that in the similar way I'll be coding this approach, and then like it's not that hard. After this all the functions we wrote, we'll be needing a temp variable as usual, start pref, because we need to keep the reference of the variable so that we can delete it later. Okay, is equal to head. Now the c is a counter variable, so because we want to go to that position, let's make a for loop instead. I less than k, I plus plus. Yeah. Now what we need to do here? Here, as you know, the prev will be slowly propagating as compared to the temp. So prev equals prev, like it's always at one stage behind that temp. So prev equals temp. Then I iterate with temp equals temp next. Okay. Now we are at a stage where, like the what to say, like prev is present at the variable before the variable we need to delete, and temp is the variable we need to delete, right? So you might say delete temp, but it cannot be done. It's pretty, like if we delete temp the link will break, right? At first what we need to do, think like presently we are here. Okay, so what are the things that we need to do? At first I need my this one to point here, then all these links we are seeing are broken, right? This thing is broken, this thing is broken. Instead of pointing here, it points directly to here. It's temp presently. Okay, and this one's prev. Okay, so now prev, instead of pointing temp, it points to temp next. So this one. Okay, so if we write here prev next equals prev next next. Okay, so if we write this, it's pretty, like it's understandable that the temp is getting out of the it, like the connectivity, and simultaneously we are deleting it. So it's what we are trying to do. And let's similarly code it up here as well. Deleted position k, second position I've tried to delete. Okay, it's already written. So let's see, 100 is deleted as we expected. So 100 was present here. So as we 0 1 2, so the third position, like 0 1 2, talking from that point of view, 100 got deleted. The iteration that took place was prev went here, temp went here, prev made pointed to this one, prev next, and this was deleted. So yeah, that's all for today. For like a homework kind of a thing, I will tell that you guys to write a simple function that delete the value, the particular value that's mentioned. That will be pretty easy. And if that's like if you have have any problem, you can connect with me. I'm in the group as well. You can DM me directly. Yeah, and tomorrow we'll be learning doubly linked list and also implementing stacks, queues, and other stuffs and some lead code questions. So yeah, that's all for today. Any problems or anything? And I'll be uploading this code in GitHub, so no problems. Oh, now I'm stopping.